characterizing when a sequence has a limit, in this case for the space of continuous functions. It's closely related to the Bolzano-Weierstrass theorem. Bolzano-Weierstrass was our infinite pigeons, finite pigeonholes, so that if I have a bounded sequence, so there's a bound, then there exists a convergent subsequence. This is for the real numbers. So a similar thing for the space of continuous functions on 0, 1, the Arzela-Ascoli theorem will show one direction, like the Bolzano-Weierstrass. The other direction is also pretty close to true. So this is a fair characterization. So we have a uniformly bounded sequence of functions. If they are uniformly equicontinuous, then there exists a convergent subsequence. Convergence in the sense of the supernorm, so uniform convergence. Equicontinuous is like continuous. X minus y is less than delta. Fnx minus fny is less than epsilon. The uniform part of equicontinuous is that delta won't depend on x or y. The equa part is that delta also does not depend on n. If it was just equicontinuous, then delta would depend on x. The proof boils down to showing that these two conditions give us that the sequence is uniformly Cauchy, and since it's a complete space in the supernorm, convergent. Looking at the converse direction, if I'm given a sequence of functions in the continuous space, if I'm given any subsequence, then that has a subsequence that converges to some function. That's the converse. Let's prove the Arzela-Ascoli theorem. So we'll start with an enumeration of the rational numbers on 0, 1. So what we're going to do is we're going to pick out a bunch of subsequences. So once I fix the first rational number, that's a bounded sequence of reals. So Bolzano-Weierstrass, it converges. So n1 is my first subsequence chooser. So it really should be like n sub k sub 1, where k1 is my first subsequence variable. But just call it n1 for brevity. Then from that, we'll choose another subsequence. So we'll go to the second rational and do it again. We'll choose a subsequence of that sequence. So n2 is my second subsequence chooser. This is basically an induction step that we just done. Given a sequence, I'm choosing a subsequence. So fn1, that converges at R1, so any subsequence of it converges to the same limit. But it also converges at a second rational. Well, now we can just do it again. That's an induction step. Just do it again. I'll pick now a third subsequence off of the n2 sequence. So it'll converge off all the things that n2 does, because it's a subsequence of it, and it'll converge on the third rational. Well, there we go. Just keep on doing it. Now I've got myself my diagonalization argument, and I can choose a diagonal subsequence of the original functions. So m equals 1 will be the first term of the first subsequence, m equals 2, second term of the second sequence, m equals 3, third term of the third sequence, and so on. My claim is that this sequence will converge for all rationals. I'll leave that as an exercise for you all. So now let's go for our uniformly coshy we're trying to find. So we'll let epsilon be given. And now that epsilon we're going to use for the rest of the proof. Because this f sub m sequence is convergent at every rational, so there's a cutoff depending on that rational number, so that the tail is less than epsilon over 3. Now we'll go ahead and use uniform equicontinuity. So at every point in the interval, there's a delta we can use. The delta doesn't depend on x. I should have written it differently, but there you go. So delta just depends on epsilon, because it's uniformly equicontinuous. And we have a continuity statement for all the m in the sequence. So the x doesn't have to be between s and t. I'm just setting it up for delta balls, and so I want x to be kind of the center of the delta ball. Okay, let's get our uniform bound going. So given any t in the interval, I want to look at the tail of the sequence. So we'll do our triangle inequality, continuity, convergence, and equicontinuity again. The cutoff only is for the second term. But the problem is I need it to depend on epsilon, and right now it depends on epsilon and x sub k. So I need to remove that x sub k dependence. Compactness to the rescue for this. Take balls of radius delta around every point in 0, 1, where the ball of radius delta, the delta is from equicontinuity. The delta doesn't depend on x. That's an open cover. 0, 1 is compact by Heine-Borel because it's closed and bounded. So there's a finite subcover. So I can enumerate some of those x's. So this x sub j is just one of the x's in the interval. But for each of those balls, I can pick one of these enumerated rationals I had. So Rkj is in that ball centered at xj. So it's a subsequence of that enumeration. There's only a finite number of those. So there's only a finite number of rationals. Well, there we go. There's my cutoff. I'll take the maximum of my enumerated rational cutoffs, the finite ones, from my finite subcover. And then for my handoff point, I'll use that enumerated rational. No matter what JI min, cutoff's bigger, and I'm done.